Hey guys, this is Miss Rains. Normally I would introduce solubility rules with a demo, but since we're not face to face, I have a short video clip that's showing the reaction of lead nitrate and I want to say potassium iodide. So you'll notice that the solution in the test tube is clear and the solution in the pipette toward the top of the test tube is also clear. But I want you to notice what happens when we actually mix the two clear solutions together. So we mix the two clear solutions together and we actually get a yellow precipitate. Remember, precipitate is just a solid that falls from solution. This yellow precipitate forms because two of the ions that are reacting form an insoluble compound. It's a compound that cannot dissolve in water. That particular compound is lead to iodide. That's that nice, pretty yellow color there. The lead comes from the lead nitrate, the iodide comes from the potassium iodide. And since they're all in solution, when they mix together, they form a bond because those two are more attracted to each other than they are the water. And then for it falls out of solution. For Chem 1, we just need to know how to use solubility rules to predict which substances will be a solid and which ones will be a aqueous or a soluble product. AP Chem, there's an abbreviated version of this that they would actually give you guys to memorize. The thing with solubility rules is most of the time you're looking at the anion, the negative ion in the ionic compound. The only time you're looking at the positive ion is if it happens to be an alkali metal or if it happens to be ammonium. Those are the only two where the positive ion would actually tell you anything about the substance, so alkali metals and ammonium. So, what these rules do is they tell you what is going to be soluble or insoluble. The thing about solubility is if it's soluble, we know that it is aqueous, AQ. If it is insoluble, we know that it's going to form a precipitate, which is just a fancy way of saying that it is a solid. So the thing with solubility rules is it's the exceptions that tend to trip students up. When things are an exception, it's the opposite of what the rule says because it's saying that I don't follow the rules. I'm doing the exact same thing. So, for example, if we had lead to sulfate as one of the products, it would be considered insoluble because it is one of the exceptions. Same thing down here if we had a carbonate with an alkali metal. So potassium carbonate, for example, it would be considered soluble, which means it would be aqueous. It would dissolve. It would not form a precipitate. So solubility is the chemical property that refers to the ability of a substance to dissolve in a particular solvent. Now, for us, we're just using our solvent is going to be water because most double replacement reactions occur in water. You can predict the formation of a precipitate by using the solubility rules for the ionic compounds. Now, your soluble substances will stay as aqueous, they stay as AQ, and your insoluble substances will form the precipitate, they form that solid product. So let's start with just looking and using the solubility rules. So if I look at my first substance, I have CsPO43. So is CS an alkali metal or ammonia? Well, technically, yes, it is. So CsPO4, since it is an alkali metal, it's a salt. Remember, salt's just a fancy way of saying ionic compound of an alkali metal. It's going to be soluble. Now, if I looked under my phosphate, I would see that it is a alkali metal exceptions, so it is also soluble. So looking at the second example, I've got AgCl. So Ag is not an alkali metal, which basically just means I'm going to have to look at my other solubility rules to determine what's going on. So I find my solubility rule for Cl, my chloride, and chlorides are soluble unless it's lead, silver, or mercury. This just happens to be mercury, so therefore it is insoluble. Next one is strontium hydroxide. Strontium is not an alkali metal, so let's look at the hydroxide rules. We look at our hydroxide rules. It says that group 1, strontium, barium, and ammonium are exceptions. That means since this is strontium hydroxide, it will be soluble. It will dissolve. Ammonium sulfide, well, ammonium's ammonium, so therefore it must be soluble. That first rule applies to it. Aluminum sulfide, aluminum's not an alkali metal, so therefore we're going to look at the sulfide. And sulfides are third from the bottom. So sulfides are insoluble unless it's an alkali metal or ammonium. Since this is aluminum, it's going to be insoluble, therefore it would form a solid precipitate. Pause the video and see if you can do the next 5 for yourself. So, next couple, fairly quickly. Lead to bromide. So if I look at my bromide rules, I can see that bromides are soluble unless they are with the lead 2 ion. Therefore, it's insoluble. Aluminum nitrates. Nitrates are all soluble. That's that second rule from the top. Calcium hydroxide. Calcium hydroxide is not one of the exceptions. Therefore, it is insoluble. Zinc acetate. So C2H3O2 is acetate. That's that second rule, and all of them are soluble. Therefore, it would be soluble. And magnesium carbonate. So look at my carbonate rule, and magnesium is not a group 1 metal. Therefore, it is insoluble. So the thing with our solubility rules is that we can actually use them to predict which product will form a precipitate in a double replacement reaction. Remember earlier I said that your solubility rules drive your double replacement reactions because we won't see a reaction occurring unless a solid product is formed. So first you would have to predict your products and make certain that you exchange ions, you balance charges. Then you check the solubility rules of the products to see which ones are soluble and which ones are insoluble. So let's look at a couple examples. We've got H2SO4 and BaCl. So it's not neutralization because we don't have the hydroxide. So let's predict our products. We know that our SO4 is going to switch places with the Cl. So I would take my SO4 and my Cl, and they switch partners. So we end up with H and Cl together and Ba and SO4. So when I balance the charges between H and Cl, I get HCl, and when I balance them between barium and sulfate, I get BaSO4. So let's look at our solubility rules. HCl, H, though technically it's not a metal, it is in the first group. Therefore, it's going to be soluble. It will be soluble, therefore it will be aqueous. Sorry, I can't talk. So let's look at our barium sulfate. So let's check the sulfate rule. Sulfate, if it is with barium, is insoluble. So sulfate would be my precipitate. So if I were to mark the phases on this particular reaction, the first two, my reactants, would be aqueous. The first product would be aqueous, and my third product, second product would be a solid. So looking at the next example, again, double replacement, you are switching partners. So my nitrate switches places with my Cl, and I have to balance charges. Now, we don't know the charge that lead forms because it could be a 2 or a 4. So I'm going to reverse crisscross to determine that lead is a 2. And I'm going to assume it keeps the same charge because we don't know how to deal with redox. So when I balance my charges, I accidentally clicked one too many times, but I get PbCl2 and CaNO3. So if I look at my chlorides are soluble unless it's at lead 2. So lead 2 is going to be my solid. It's going to be my precipitate. And my CaNO3, so look at my nitrates. Nitrates are all soluble, therefore it's not going to be aqueous. It is not going to form a solid. Last but not least, double replacement reaction. Remember, we got to think square dance. So my PO4, that polyatomic, switches places with the Cl. Cl comes over here. Hopefully you recognize table salt, so we know that product's NaCl. Chromium has a charge of 3. Phosphate has a charge of 3. Therefore, they balance out. End up with chromium phosphate, CrPO4. So, shouldn't have to check the solubility rules for table salt because we know that table salt can dissolve in water. So we know that this is going to be aqueous. Let's double check my chromium phosphate. Phosphate, PO4, are insolubles unless it's an alkali metal or ammonium. And that is definitely not an alkali metal. That's a group 13 metal. Therefore, that must be my solid product. Now, the thing with double replacement reactions is don't let these 3 examples make you think that you always have only one precipitate. Sometimes you might have nothing that precipitates out, and every once in a blue moon, you might actually get 2 precipitates. That is it for today.